So solutions are, well, mixtures of two things, two or more things. If you remember, we had homogeneous and heterogeneous mixtures from the beginning of the semester. Keyboard's in the way. So a homogeneous mixture of two or more substances is a solution. So these are things that are mixed, and it's mixed evenly throughout the whole thing. Solutions are very common. In fact, it's very unlikely that you've ever had any water that was not a solution of some degree. In fact, this is what companies like Aquafina, right? I think Coca-Cola owns Aquafina, or Dasani, one of those. Pepsi owns the other. They actually take water, filter it all out, and they add minerals back to make a solution, because that solution of minerals tastes better than pure water actually does. And pure water would actually not be good for you, because we need those salts that are in those solutions. So the ocean is a solution of salt and other solids dissolved in water. That's why you can buy sea salt, and it does taste a little different than regular salt, table salt. Blood plasma is also a solution, and it has several solids as well as some gases. So what we're going to see is that solutions don't just mean mixtures of a liquid plus a solid, but we can also have a liquid plus a liquid, or a liquid plus a gas, or actually we can have all three. Ultimately, though, the resulting mixture, the resulting homogeneous mixture, will be a solution. Or sorry, will be a liquid. The resulting solution will be a liquid. Some common types of solutions, because we can have a gas and a liquid, liquid and a liquid, or could actually have a solid and a gas, or other combinations. The most common ones are really going to be gas and gas, gas liquid, liquid liquid, and solid liquid. All right, so vodka, ethanol and water. Soda water is CO2 and water, right? So any soda that you've ever had, anything that's carbonated, that's going to be either CO2 and water or nitrogen and water. That's what a nitro cold brew is, if you're into coffee. You can have also solutions of solids, which are called alloys. So those are just some common types of solutions. I'm going to try and move quickly through the things that I don't think are as important, and we're going to try and spend more time on the things that are going to be directly important, because we do need to move quickly here. So this is one of the things that's important, is knowing the two components of a solution. So we have our solvent, which is the majority component, and we have the solute, which is the minority component. So there's less of it in the solution. In a solid liquid solution, the liquid is usually considered the solvent regardless of the relative proportions of the components. So if you have a solid, we always call that the solute when it's in another liquid. This is because some things, like sugar, particularly fructose, is more solute, or you can dissolve more fructose in water than there is water. So you can have 100 grams of water, and you could have, I think you can actually have 200 grams of fructose. I could be wrong on that. But you can have more fructose by mass than there is water. Water would still be the solvent. Fructose would be your solute. It's just really a matter of convention. If you have two liquids, it's different. Then it's the majority component all the time. So the most common solutions are those having water as the solvent. Definitely in this class. If you do organic chemistry, you'll work with other types of solvents. But these are aqueous solutions. We've come across this a few times. In a chemical equation, you'll see it written as something like NaCl. That's what that AQ means. It means aqueous or dissolved in water. Aqueous equals dissolved in water. Other solvents are also used, especially to form solutions with nonpolar solutes. This is why things like paint thinner is a nonpolar solvent for nonpolar solutes. In that case, it would be the paint. Or nail polish remover. Well, nail polish remover is technically polar. But paint thinner is a nonpolar solvent. And this is important that we have different types of solvents because as we sort of like went over this very briefly in the previous chapter, but like dissolves like. So polar solvents dissolve polar solutes. So polar solvent will dissolve polar things. Nonpolar solvents will dissolve nonpolar things. Some other toluene is a paint thinner. But these are also other nonpolar solvents here, hexane and diethyl ether. It's not super important that you know these specifically, but they are some examples. Acetone, as I was mentioning, is a polar solvent, also known as nail polish remover. Not all nail polish remover is acetone, but I think acetone works the best. Methyl alcohol is also another polar solvent, and ethanol would fall into that list as well. So this comes back to when we were talking about ion-dipole interactions. Ion-dipole from chapter 12. And this is how water dissolves a lot of ionic solids. So things like sodium chloride. There's a competition between the solvent and solute attractions and the solute-solute and solvent-solvent attractions. So to kind of translate it from those new words there, and actually this graph is very nice. So the attractions between the water molecules are in competition with the attractions between the salt atoms, right? So our sodium and chlorides, and then are also in competition with the water's attraction for the sodium and the water's attraction for the chlorine. So if the attraction between the water, so if, maybe I can write it like this, if this is stronger than this, it will be soluble in water. So in this case, we do know that sodium chloride dissolves in water. Table salt dissolves in water. So that means that the bond, or the attraction, I shouldn't say bond, the attraction between the water molecules and the sodium and the chloride ions is stronger than the attraction between the sodium and the chloride ions to each other. So the water molecule can get in here and take apart all of those sodium and chloride ions and pull them out into the liquid. But in the case of calcium carbonate, so if we replaced the sodium here with calcium, and over here we replace this with carbonate, the bond between, or the strength of the attraction between the calcium and the carbonate is stronger than the attraction of the water between the calcium and the water and the carbonate. So the water is not strong enough to pull apart those ions, and so calcium carbonate doesn't dissolve in water. And again, these are also all intermolecular forces, which is why chapter 12 was important for this. So in the case of these again, these are ion-dipole interactions. The positive end of the water is attracted to the negatively charged ions, or the chlorine. And the negative ends of the water, which again have dipoles, are attracted to the positively charged ions, in this case, sodium. And this is actually an example. This is going to come up later, but I want to introduce this now. This is an electrolyte solution. It's actually a strong electrolyte. And it's a strong electrolyte solution because the sodium and the chloride are being separated when they dissolve in that solution. If you remember all the way back to our net ionic equations, that's where we took these strong electrolytes, things like NaCl. So yeah, we took things like NaCl, and then in our net ionic equation, because this is aqueous, we write that as Na plus Cl minus in our solution. So those individual ions actually get separated. So the solubility of a compound is defined as the amount of the compound, usually in grams, that dissolves in a certain amount of liquid. So we're going to start out talking about this certain amount of liquid is usually going to be 100 grams of water. Sorry. Just almost sneezing. Okay, so the solubility of sodium chloride at 25 degrees C is 36 grams per 100 grams of water. So if you have a kitchen scale, you could measure out 100 grams of water, and you could pour 36 grams of salt into that. And at 25 degrees C, which is just a little bit, well, it's a little on the warm side. That's like 78 degrees Fahrenheit or something. It's like 78 degrees Fahrenheit. And so if your apartment is that warm, which especially in the summer it probably is, you should be able to dissolve all 36 grams in your 100 grams of water. If you add any more than that, and this 36 grams in 100 grams of water, that's a saturated solution. This is another one of those things that is very important, especially for the lab, which you might have seen before class, just right before class. I did make an assignment for that, and it's not due. It's due for everybody on Monday. So you have the weekend to finish that. This is going to be one of those important points, though. A saturated solution holds the maximum amount of solute under the solution conditions. So in this case, that's 36 grams of NaCl under the solution conditions, which is going to be 100 grams of water at 25 degrees C. Any additional solution, any additional solute added to a saturated solution will not dissolve. So if you add more, it will not dissolve. So the opposite of a saturated solution is an unsaturated solution. So that's less than the maximum amount of solute. And you know you have an unsaturated solution because if you add additional solute, it will dissolve. So we haven't reached that maximum point yet. There are ways to make a supersaturated solution where your liquid, your solvent, is holding more solute than its normal maximum. Most of the time, we get a precipitate. That word should be familiar. Right, so precipitate is where we have a solid coming out of a liquid. Supersaturated solutions can form under special circumstances, such as the sudden release in pressure that occurs in a soda when it's opened. So because the soda is being held under high pressure, that allows more gas to be dissolved in it. And then when you release that pressure, that gas can come out. I do have, I got a YouTube video here. I think I've mentioned this in class before, maybe also. This is, whoops, switch over here. This is sodium acetate. No, I don't want that. Let's just do it like this. Properties. Here we go. All right, so this is a sodium acetate solution, and it's supersaturated. So there's more sodium acetate, which is a solid, dissolved in this water than normally would be able to be dissolved. And so what they're going to do here is they're taking a spatula, and I think, you can actually see my mouse on this. So they're taking the spatula, coming in here, and it's got a little crystal of sodium acetate on it. And as it goes into the solution, that sodium acetate is now able to form crystals very quickly from that newly introduced crystal. So that's all solid sodium acetate being formed in there. There's another video. There's another video here. Let's see. I thought this video had both things, but it does not. Yeah. So you can do a lot of cool stuff. So there's like a toothpaste and a sodium acetate solution. All right, so it's forming a solid really, really fast. Here's the, it also gets hot when you do this. Just measuring the temperature. Oh yeah, this is the one I was looking for. So when you pour it out also, as it hits the counter or the dish or the other sodium acetate, it also quickly precipitates. And there's so much dissolved in the water that the water is actually getting trapped in those crystals as well. You might have experienced this also or seen this on, some social media or whatever, where I think Coke, especially, when you put it into, well, sometimes when you put it in the freezer, sometimes. If you're going to do this, do it with a plastic bottle because they're much less likely to explode. When you put it into the freezer, if it's left in there stable enough without being shaken around or bumped or jostled at all, it will super cool. So similar to supersaturating, it'll get colder than the freezing point. Then when you take it out, you can like knock it on the counter and the whole thing will freeze, but it'll be like a slushy-like consistency. I don't know the specifics on how to make that happen. You'd have to look it up. So the solubility rules, though, that we talked about before, those give us a qualitative description of the solubility of ionic solids. So qualitative here means that we can say, yes, it dissolves, no, it dissolves. We haven't learned anything about how much can be dissolved. Some ionic compounds like calcium carbonate are insoluble because the attraction between ions is greater than the solvent-solute attraction. So that's where, again, that tug of war between the water trying to pull the calcium and the carbonate apart. But we can have molecular solids also be soluble in water depending on whether the solid is polar or not. So remember, ionic compounds, that's again things like sodium, which is a positive ion, and chlorine, which is a negative ion. Those ionic compounds are made up of lots of sodiums and chlorines in a 1-to-1 ratio, again, in a large lattice or array. Molecular solids consist of individual molecular units at specific ratios of atoms. So table sugar is a polar molecule that's soluble in water, but nonpolar solids such as lard, vegetable shortening are insoluble in water. This is why if you cook like ground beef and you get that leftover fat, that's when it's hot, it's a liquid. That's why you can't pour that down the drain, because as soon as it goes down the drain and cools, it solidifies, and it's a fat, so it's a nonpolar solid, and it can clog your drain because the water that you send down the drain isn't going to dissolve it. So here's that concept I said was going to be introduced later, this idea of electrolyte solutions and non-electrolyte solutions. So electrolyte solutions, this is the key, contain dissolved ions. So these are going to be from ionic solids or ionic compounds. Non-electrolyte solutions are going to come from molecular solids. So our sodium chloride here, here's our sodium ion, here's a chloride ion, right? So all the blue ones are sodium, all the green ones are chloride. They are going to be in this solution separate from each other with space in between. Contrasted by these sugar molecules, when the sugar dissolves, each unit of sugar, which was it on the previous page here, C12, so it's C12, H22, was it O11? So that's how many carbon, hydrogens, and oxygens are in each sugar atom or sugar molecule. These will be floating around as these units. So if I zoom in on this, right, we can see that these are made up of the individual atoms. Whereas our ionic or electrolyte solution has the separated ions. So if you've done the lab, or started the lab at least, part of it is to play around with these electrolyte or non-electrolyte solutions, which you'll see Andy doing in the video. Oh, I guess we're going to come back to that. They conduct electricity, that's what I was going to say, but solubility is variable with temperature. So in general, this is not the case for everything, but in general, solubility of solids in water increases with increasing temperature. So sugar dissolves more easily in hot tea than iced tea, or iced coffee, or any cold beverage that you might want to put sugar in. And the temperature dependence of solubility varies depending on the substance. And I believe this is another part of that solubility lab, specifically with the post-lab, I think it's the post-lab questions, or the critical thinking questions. It asks you about, how much of this is soluble in, or this much of some substance in this amount of water at a certain temperature. Is it saturated, supersaturated, or undersaturated? And the way that you read this graph, actually, let me go to the next slide here, because we're going to do some of these on the Mentimeter quiz. I'll leave this full size for now. Let me pull up the Mentimeter quiz over here at the same time. Somebody's already answering. That's fine. So the way that you read this is these are all listed here, the solubility, and these are all the amount of each of these substances in grams that can be dissolved in 100 grams of water. Okay, so if I want to zoom in on this graph, let me find one that like crosses a nice intersection. Is there one? Okay. So for potassium chlorate here at 70 degrees C crosses right here. So we can have 30 grams of KClO3 in 100 grams of water at 70 degrees C. And this would be saturated. If we're above that line, so if we had, let's say, 35 grams of potassium chlorate, that would be a supersaturated solution if all of that dissolved. If it's below that line, if we had 20 grams of potassium chlorate at 70 degrees C in 100 grams of water, that would be an undersaturated solution. So the questions here on the Mentimeter quiz are related to this and these examples. I didn't think that through super well, but I don't really want to make this smaller. I can make this smaller though. I can make this bigger actually. Okay, so using this graph, hopefully that's not too small. So using this graph, if we have 50 grams of potassium chloride, so that's this line, this purple line, 50 grams of potassium chloride in 100 grams of water at 50 degrees C, is that saturated? Or sorry, is it undersaturated or is it supersaturated? Assuming it all dissolves. I'm actually going to just put a, whoops. It's 30 seconds on that. So really you're looking at, is it above the line or is it below the line for those coordinates? Maybe we can do 10 seconds for these even, I don't know. All right, so this is counting down 50 grams and 100 grams of water. And one of the things that's important to note here is that this graph only works directly if we're using 100 grams of water here. So we'll go over to 50 degrees Celsius, and then we'll go up to our KCl line. And so it looks like just above 40 would be saturated, but we're at 50. So at 50 grams of KCl in 100 grams of water at 50 degrees C, that would be supersaturated because that point is above the potassium chloride line. All right, next one then. I'll do 30 seconds here again. Okay, so now we're looking at 10 grams of potassium chlorate in 100 grams of water at 70 degrees C. Oh, I should delete this. So again, this orange line here is potassium chlorate. And 70 degrees C, so it's 10 grams below that line at 100, or at 70 or above. 6 of you were able to vote in time. 100% hit on that one, thank you. Yeah, so this would be undersaturated because 10, again, is right here, and it is below the line of saturation for potassium chlorate. Another one of these. So just moving on to this next one. So 40 grams of sodium chlorate, or sodium chloride in 100 grams of water at 30 degrees C. Just put a little countdown timer on it. And again, these are completely anonymous. So, well, I don't want you to just outright guess. It's fine if you don't get it right. Oh, the Menti code, yeah, it's really hard to see there, isn't it? 55700694. Okay. Yeah, so for sodium chloride now, we'll find 70 degrees C, or sorry, not 70, 30 degrees C. And then we'll go up to 10 grams. And that's on the line for potassium chlorate, but we're talking about sodium chloride here. So it's well below that line. Oh, sorry, 40. 40.
Yeah.
Yeah, so 40 is above the line. My apologies. It's super saturated. All right, so these next two are a little bit more difficult because we don't have 100 grams of water. But this is where you can convert this so that you know what it would be in 100 grams of water. The reason that this isn't 100 grams of water is because that's a convenient amount of water to work with. But you could convert these fairly easily. So actually, let's do this. So this is the way you would do this. So this is 25 grams of KCl in 50 grams of water. So if you wanted to know how much potassium chloride that would be in 100 grams of water, all you have to do is multiply the top and bottom by whatever would make the bottom 100 grams of water. So since it's 50 grams of water on the bottom, if we multiply by 2 over 2, that'll be 50 grams of KCl in 100 grams of H2O. And then that's what we use and find on this chart. So potassium chloride is this purple line again. We're looking at 90 degrees C, and we're looking at 50 grams of water, or 50 grams of potassium chloride. So that would put us right here, and that would be undersaturated. So just know that when you're working with, and this is true for the lab, when you're working with one of these solubility graphs, you got to make sure that your per whatever grams of water matches the graph, which will usually be 100. And then again, just to reiterate, I multiplied both by 2 because multiplying 50 by 2 would make the 50 grams of water 100 grams of water. And then we just multiply the top, the numerator, by the same. So for this next one, what? That's the end of the presentation? Oh, I didn't put it in here apparently. Okay, well I guess we'll just do this one. So we got 90 grams of potassium nitrate, but it's in 200 grams of water. So we got 90 grams per 200 grams H2O. So just like in this first one, where we multiplied both by 2, because that made the numerator, or the denominator, 100, we can also divide to make the denominator 100, as long as we divide the top and the bottom by the same thing. So it's multiply, multiply. And then here we're just going to divide the top by 2. We're going to divide the bottom by 2. So we're going to end with 45 grams potassium nitrate per 100 grams H2O. Dad's calling. He knows I'm teaching. Or he should. I'll leave a message if it's important. Okay, so then we can go to our graph and we can look at our temperature, 40 degrees C. So 40 degrees C. This is the potassium nitrate curve up here. And if we go up to 45 grams of potassium nitrate, oh, actually, I didn't think that one, oh, no, sorry, 40. 40C and 45 would put us right about here. So that would be undersaturated. Okay. That was the only thing I had time to put together for the Mentimeter quiz. I gotta modify these slides more so that those things fit in better. You can use this fact that solubility varies with temperature to get more pure compounds through a process called recrystallization. And this is actually like making rock candy. So if you have a saturated solution that's prepared at an elevated temperature, as that solution cools, the solubility decreases, like we saw on all of these curves, right? So at high temperatures, you can dissolve more, but as the temperature decreases, so does the solubility. This also happens for sugar and for a lot of things. So as that solubility decreases, some of the solid will precipitate from the solution. And if you do it slowly, the solid will form crystals as it comes out. And those crystals don't want to include the water or whatever else is in your solution. They want to keep that out. So they will, as they're slowly collecting into these crystals, be pushing out all of the other impurities, and you can get really nice pure solids. Which is what they do in Breaking Bad, actually. But you can also use it for rock candy. I did try to do this recently as a demonstration for my nephew, but I didn't realize that it was going to take like 2 or 3 days for it to crystallize. Basically, though, you take sugar and you boil water, and then you pour sugar in until the sugar doesn't dissolve anymore. And then you put a stick or a string or something into the liquid and wait for it to crystallize. It takes a long time. All right, so for solutions of gas and water, if you ever used a soda stream, right, this is the same thing. A can of soda is an example of a solution with a gas is dissolved in a liquid. And the way they do this for soda is that they just add a lot of CO2 into a very high pressure vessel, the can, and that dissolves the gas into the liquid. And most liquids exposed to air contain some dissolved gases, but it depends on the temperature. So lake water and seawater both contain dissolved oxygen, which is necessary for the fish to survive. And then our blood also contains dissolved nitrogen, oxygen, and carbon dioxide. And then tap water, if you've seen this before, sometimes when you get tap water, or if you go to somebody's house and you pour the tap water, it comes out super, super cloudy at first, but if you just wait long enough, most of that cloudiness disappears. And that's because that cloudiness is because of dissolved gases. So the solubility of gases and liquids decreases with increasing temperature, which is the opposite of solids. So warm soda fizzes more than cold soda because the solubility of the dissolved carbon dioxide gas decreases with increasing temperature. So this should not be anything necessarily groundbreaking, right? But generally, solids exist at lower temperatures, and gases are higher temperatures, and then liquids in between. So when you're thinking about, how does temperature affect the solubility of solids and liquids versus how does it affect gases and liquids? As you increase temperature, so for solids in liquids, as solids in that liquid get warmer, as they get more like liquids, solubility increases. So as you increase temperature for solids, they get more soluble in liquids. For gases, you would have to cool that gas down to make it a liquid. So here, as you cool the gas to get closer to being a liquid, it becomes more soluble in liquids, and solubility increases. This was something that was helpful for me, right? So if you get a gas colder, it will be more soluble in a liquid because it's becoming more like that liquid as you cool it down. And for solids, as you warm them up, they get closer to being liquids, and so they become more soluble in the liquid. But as your temperature moves farther away from being a liquid, those get less soluble. So for gases, that's increasing temperature. For solids, that's decreasing temperature. So you can do this at home, actually, and sometimes this has gotten me before, but before water actually reaches its boiling point, those gases that are dissolved will come out of the solution first, and it can look like it might be boiling, but it's not actually boiling. It's only once it comes to a roiling boil with more vigorous boiling that's the actual water evaporating or turning into a gas. Vaporizing, that's the word I was looking for. The solubility of gases also depends on pressure, so it's not just the temperature. And this is one of the things that kind of just made sense for me, but the higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid, or the more of the gas will dissolve in the liquid. And this happens just because there's more of the gas. So it's, in some ways, if you add more gas and more pressure, right, because remember that Dalton's law of partial pressures, right, so the pressure total is equal to the partial pressures of the things that make it up. So if you increase the pressure of something, you're adding more atoms into that, container. So more of them will dissolve into the solution. It would be just like dumping more sugar into water. More of it's going to dissolve into the water. And so this is how they pressurize sodas and how they add CO2. Sorry, this is not how they pressurize. This is part of why they pressurize sodas, is because that adding that CO2 pressure dissolves it into the liquid so that it's fizzy when you drink it. And a soda stream works the same way. It's 6 o'clock, and we are at slide 22. Awesome. A can of soda is pressurized with carbon dioxide, which actually, if you look at like the design, if you like design, if you like the show How It's Made, which maybe is an old show at this point, look up how soda cans are made and why they are designed the way they are. It's pretty interesting. When the can is opened, the pressure is released, and it lowers the solubility of carbon dioxide in solution. And that's why it starts fizzing. And actually, by shaking a soda can, you're shaking it actually is removing more of that, or is actually causing some of that gas to come out of the solution before you even open it. And it increases the pressure, so when you actually open it, that's why it explodes. You're essentially prepping all of that to leave. Okay, coming into some of these more of these numbers though, and some of the things that we're going to have to do calculations. This is just the first one, but we can specify solution concentration using mass percent. This is another reason that we use 100 grams of solution before for that graph, because a solution with a concentration of 14% by mass contains 14 grams of solute per 100 grams of solution. So our mass percent here, oh, actually, sorry, this is a little bit different from the thing from before, but so the mass of the solution, excuse me, sorry. The mass of the solution is the mass of the solute plus the mass of the solvent. Or I should just say solution equals solute plus solvent. So not the mass of the solvent, which would be just the water. This is the mass of the entire solution. Okay, so if we want to calculate the mass percent of a sucrose solution containing 11.3 grams of sucrose and 412.1 milliliters of water, we're going to assume that the density of the water is 100 grams per milliliter. And this is a unit that you've probably forgotten about, but is going to come back. And it's going to come back in force. So if we have the mass of sucrose, but we have the volume of water. So milliliters is a unit of volume. If you want to use our mass percent, so mass percent is equal to the mass of the solute divided by the mass of the solvent times 100, we need to calculate the mass of water that we have, and we can do that using density. And that's because density is in grams per milliliter. So if we have 412.1 milliliters of H2O, we can use our density as a conversion factor, and that's 1.00 grams per, and that's grams of H2O, per 1. Per 1 milliliter. So it's 4.12.1 times our 1 gram per 1 milliliter. So milliliters of H2O cancels. And this is 412.1 grams of H2O. Not everything has a solubility, or sorry, a density of 1, but water under the right conditions does. Okay, so that's the mass of our sorry, I meant to write it like this, the solution. This is the mass of solvent. And we were given the mass of the solute. That's our 11.3 grams of sucrose. So we're going to put 11.3 grams divided by 412.1 grams of H2O plus our 11.3 grams of sucrose. Because it's the mass of our solution in the denominator, not the mass of our just solvent. Not just the mass of the solvent, and then multiply that by 100. And this is one of those things where I do want to emphasize you need to put parentheses around this addition. Otherwise, you'll get the wrong answer. So 11.3, sorry, I keep bumping this. 11.3 divided by, and then parentheses, 412.1 plus 11.3, and close those parentheses. So this is a, never learn to leave enough room. So this is a, and then sorry, multiply that by 100. and we keep 3 sig figs. So this is a 2.67% sucrose solution. So the trickier part of these problems is just going to be usually getting the mass of your water or whatever the solution is using density, which is kind of something we haven't covered in a while, but it's also a conversion factor. So you should hopefully know how to use it. Are there any questions on this? Okay, cool. Keep going. Some other commonly used units, these ones we're not going to use very much here, but you've probably seen them before. Parts per million, well, parts per 100 is the same as percent. Parts per million is the grams of solute per 1 million grams of solution. So our parts per 100 was grams per 100 grams of solution. And then parts per billion is grams per 1 billion grams of solution. So then we can use, when we have a mass percent, we can use that as a conversion factor between the mass of the solute and the mass of the solution. And like so many other things that we've done, you need to write the mass percent as a fraction. So you'll always take mass percent and divide it by 100 grams of solution before you use it. It's because percents are convenient, but they need to be converted to proportions or fractions first. Okay, so this is similar to our previous question, but now we sort of flip the script. And we're asking how much sucrose in grams is contained in 355 milliliters, or a 12-ounce soft drink containing 11.5% sucrose. And we're going to assume a density of 1.04 grams per milliliter. And I will usually write this as 11.5% by mass. So really we're going to start here with the one thing that's not a conversion factor, and that's our 355 milliliters. Right? Because remember, percent mass is a conversion factor between mass of solution and mass of solute. And, whoops. Our density is a conversion factor between grams of solution and volume of solution. So if we start with 355 milliliters of soda, or soft drink, to use mass percent, and again, we're going to convert this, this will be 11.5, well, 11.5% is the same as saying 11.5 grams of sucrose per 100 grams of solution. Or you can just take that and divide it by 5. Or, sorry, not 5. Take 11.5 and divide it by 100. So we need to get into mass in order to be able to use this. And I keep, sorry if that's loud, the bump in there. 355 milliliters, so we need to convert this into mass, and we're going to use our density to do that. So we want grams, so this is going to be 1.04 grams per 1 milliliter. So our milliliters will cancel, and we'll get 355 times 1.04. So it's 369.2 grams of soda. And then we can use our 11.5 0.5 grams of sucrose divided by 100 grams of solution. So 369 times 2, sorry, 369.2 times 11.5 divided by 100 means that we've got 42, and we're only got 3 sig figs throughout here. So it's going to be 42.5 grams of sucrose. So ultimately, these problems end up just being conversion problems, unit conversion problems again. And if you're looking at the units and you remember how to convert them, all you got to do is use the conversion factors that cancel out the units that you have and give you the units that you want. Ooh, running out of time fast. One of the more common units, though, that we actually use in chemistry, mass percent gets used a lot in industry, but molarity gets used a lot more in the lab. So the difference between this and our previous is that we now have somewhat more mixed units. So we have moles of solute, so that's moles of the thing dissolved, per liter of solution. So that's similar to mass percent, where we had the grams of our solute per grams of solution, but now we've got the number of moles per liter of solution. All right, so liters of solution, not liters of solvent. And this is one of those units. Just make sure, like my advice honestly is just to write this out on every exam. And if you're on a problem that's dealing with solutions and you get stuck at some point, just look over to it, because it's so easy to forget that molarity is moles per liter. And it's a conversion factor. So it's a units of concentration, it's a unit of concentration, but it's also a conversion factor. So if you wanted to make a solution of something of a specified molarity, right, you want a particular number of moles and a particular number of liters. You add your solute into a flask first, and then you add water until you get the desired volume of solution. So these are volumetric flasks, so they're very, very accurate flasks. And so here we're adding, if we want a 1 molar solution, right, 1 molar solution of sodium chloride, you add 1 mole of sodium chloride, so you could weigh that out pretty easily, 58.44 grams. And then you add water into your flask until it reaches this measurement line, which is exactly 1 liter. I should say exactly 1.00 liters. And then you mix that so that you get your completely dissolved, completely mixed solution. Okay. So we can calculate the molarity of a solution made by, so let's say somebody makes a solution, they just tell you that they have 55.8 grams of sodium nitrate, and they're diluting that 55.8 grams to 2.50 liters. So your final solution is going to have 2.5 liters in it. The first thing that we're going to do is write out molarity equals moles per liter, because this shows us how we're going to solve this problem. So we have our liter of solution, or we have how many liters of solution. That's liters in molarity. But we need to convert this into moles. And we can do that fairly easily using the molar mass of sodium nitrate. Pull the periodic table. So sodium. This one doesn't have the masses on it. Great. All right, we don't need Mentimeter anymore. We can do a different periodic table. And we do this. Then you do this and this. Okay. That's right. This one doesn't really zoom nicely. Okay, so sodium's 22 point. So again, been a while since I've actually written this out for you guys, but sodium, nitrogen, and oxygen. You have 1 sodium, 1 nitrogen, 3 oxygens. So sodium is 22.990. And then nitrogen is 14.007. And oxygen is going to be 15.999. I know we usually use more abbreviated numbers, but so this will be 22.990. Oh, sorry. So we got the masses written there on the bottom left. This one's going to stay 14.007, and then we'll get 3 times 15.999. This is 47.997. And then we just add all of those together. And 990. So the molar mass of sodium nitrate is going to be 84.994. Okay, so, and remember, that's grams per mole. So if we want moles here, we're going to put that 1 mole on top, and that means we're dividing by 84.994 grams sodium nitrate. So 55.8 divided by 84.994, and that's going to give us 0.656516931 moles of sodium nitrate. And now we can just take, because molarity is moles divided by liters, we now know how many moles of sodium nitrate went into the flask, and we know how many liters it's being diluted to. So we can take that 0.6565, yada, 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 and divide it by 2.5. Hopefully that's not too loud every time I do that. It's because my chair's sinking. Okay, and that is going to give us 0.26. And now we're going to write it with the correct number of sig figs. So 0.263 molar sodium nitrate. Any questions on that one there? Okay. Excellent. So we can use molarity as a conversion factor between moles of solute and liters of solution. So we could determine, okay, I just want to make sure that wasn't the same thing on both sides. We can determine how many grams of sucrose are contained in a 1.95 liter solution of 0.781 molar sucrose. So remember, molarity, M molarity equals moles per liter. So this 0.781 is 0.781 moles of sucrose per 1 liter of solution. So if we have 1.95 liters of solution, we just multiply 1.95 liters by our molarity. So liters of solution will cancel, and we'll know how many moles of sucrose there are. 1.95 times 0.781. So that's 3 sig figs, 1.52 moles of sucrose. And then you could calculate the molar mass of sucrose and use that to find how many grams of sucrose there were from the moles. Yeah, okay. We'll do this one last example, and then I think next time we'll be able to finish this and then start on chapter 14 on Tuesday. So how many liters of a 0.225 molar potassium chloride solution contains 55.8 grams of potassium chloride? So again, remember, molarity equals moles per liter. So that means that 0.225 molar KCl is 0.225 moles of potassium chloride per 1 liter of solution. And we also know that we have 55. Well, we want to know how many liters of solution would contain 55.8 grams of KCl. So we're going to want to convert this into moles. And the reason that we want to do that is because liters of solution is part of the unit here for molarity. So if we can convert this into moles of KCl, then we can take this moles of KCl and use our conversion factor here, and we can cancel out moles of KCl to get liters of solution. So again, to convert from potassium chloride, grams of potassium chloride to moles of potassium chloride, we're going to need the molar mass. So potassium is 39.098. I'm just pulling this off the periodic table. And chlorine is 35.45. So because we just have one of each of those, we can add those together. So the molar mass here will be 74.548 grams per mole. So now we can use that to calculate how many moles of potassium chloride we have. So that's, well, we want to get moles. So 1 mole KCl. And we're going to multiply by that. So we're going to multiply by 1 mole of KCl over 74.548 grams of KCl. So 55.8 divided by 74.548 is going to be 0.7485 moles of KCl. So if we have 0.7485 moles of potassium chloride, and we want liters of solution, we can use our molarity, and we can say we want however many liters of solution. And so we can flip this, and it's going to be, we're going to cancel out this 225 moles of potassium chloride. So we take our 0.7485, divide by 0.225, and this is going to be 3.33 liters of solution. So if you had 3.33 liters of this 0.225 molar potassium chloride solution, that would have 55.8 grams of potassium chloride dissolved in it. I know I went a little bit fast there. I will be, again, doing like an office hour before classes next week. I'm feeling much better today, and we'll hopefully continue to improve and should be good to go by next week. So we'll be back in person next week, unless something changes, and then I'll post an announcement. Are there any questions on this chapter, stuff we've covered so far? We can go back. Okay. If there's no questions then,